Hello everyone. I am recording this video for those students who are interested in Simulink modeling of 2 degree of freedom system for analysis or for any other purpose. This tutorial will help you to understand about the underlying theory of mechanical vibration, and you will be able to see the two modes of the 2 degree of freedom vibration system. So we will discuss the free vibration case, and we will also discuss the force vibration in terms of the natural modes and the resonance. So we will be actually using the variable input frequency and to see uh, how is the input frequency linked with the true natural frequency of the system. So here is a simple example of 2 degree of freedom system. We have two masses. Two masses are attached with different dampers and different springs, and x1 and x2 are the two coordinates which can completely describe the system. So two masses, each mass has 1 degree of freedom system. So overall this whole system becomes 2 degree of freedom system. As a general rule, the total number of degree of freedom of system is equal to the number of mass each system has and the number of individual degree of freedom for that mass. In our example, we have two masses. Each mass can move in one direction only. So overall, we have a 2 degree of freedom system, and the two natural frequency are omega n1 and omega n2. I will show you the simulation in which we can use the suitable initial excitation, initial condition to excite any one or the second mode of the system. And during the free vibration at one of the natural frequency, the amplitude of the 2 degree of freedom system are related in a specific manner. So I will also explain the concept of natural mode and the principal mode. And at the end, we will also discuss one force example in which I will apply different input frequency and see how is it possible to see the resonance at the first natural frequency and the resonance at the second natural frequency. So the objective of this video is we will quickly review the theory of 2 degree of freedom system. Then we will switch to the Simulink modeling of 2 degree of freedom system. If you have followed my previous video in which you can learn how to model a single degree of freedom system, then this is a succession of those video series, and it's very easy to understand how to model 2 degree of freedom system. Particularly, the underlying theory can be very well understood if you play with different initial condition, and we would like to see what initial condition can be used to excite the first mode and to excite the second mode. And similarly, the last example would be to have some input forcing function, applying some force in different frequency and changing the magnitude and see how the system behaves. So this is a generalized 2 degree of freedom system. There are two masses attached to different springs and damper to the ground and to each other. And then we can draw a free body diagram in which we can show different forces and different uh, magnitude of the forces. So here is actually the spring forces and the damper forces linked to the masses. So here, for example, this force is a force which acts on both masses M1 and M2. Similarly, this damper force act on both M1 and M2. And for M1 and M2, the direction of this force will be opposite. right? So for the M1, if this force is acting to the right, then for M2, the same force will be acting to the left. And because we have two masses, so there is possibly four set of initial condition. For each mass, we can have initial position and initial velocity. This makes the total number to be 4. So if we derive those equation, we will have a system of differential equation where we will have two equation. Slightly rearranging, we can write them in this form where we can convert those into a mass matrix, a damping matrix, and a spring coefficient matrix. So if we rearrange in this manner, we can clearly see that the mass matrix is just like shown here. The damper coefficient matrix is here, the stiffness coefficient is here. And here are the position vector, column vector, the velocity column vector, acceleration column vector, and force vector. So that was a general overview. Now we will actually model a very simplified case in which there is no damper present and there are no applied force. So the first case is to see how can we model a 2 degree of freedom system in which there are no dampers and no applied force. So the same equation will actually translate into a simplified one like this one. In this case, we will actually assume that both masses move in a harmonic manner. So the response can be assumed to be like this. For M1, we can expect a motion similar to this one, in which capital X1 is the amplitude of mass M1, X2 is the amplitude of M2. And if we write them in the equation form, so those two equations, removing the damping, removing the input force, will translate into this one. And for the modeling part, we will slightly rearrange those equations into those two equations. So considering the first equation, we will bring everything, those two terms we will bring to the right. And so if, let me just show the screen. So if this is the equation, then we can rewrite this equation in this form, right? We can bring those two terms to the right side. So the right side would be like this. And then finally we can divide it by m1. So that would be the x1 double dot. So similarly, we can also rearrange the second equation. And now we would like to shift to the Simulink and see how can we model this those two equations. So let's jump on to the Simulink. So here I have already developed the Simulink model, and here let me remove this annotation. So here actually, if this is the first equation, so this equation can be modeled by this block. So here we have x1 double dot. So those three signal, it's actually the zero force, and this one is K2 time x2, and this is actually the other term, which is k1 plus k2 into x1. So x1 signal is taken, it is multiplied with k1, then provided here. X1 is taken, multiplied with k2, then provided here. So the sum is compiled here with a negative sign. So this becomes the x2 double dot, x1 double dot. Then if we integrate it, it becomes x1 dot. And integrating this one more time, we would get x1. We can clearly see that there is actually x2 involved with the multiplication of k2. So here is x2 here and being multiplied with k2, and we have that signal as well. This link is actually the reason of both masses are coupled in some manner, right? So similarly, if we just see the bottom part of this model, it's about the M2. So this is the modeling of M2. We can clearly see there are three forces, and then we divide it by M2. So this is 1 divided by M2, all the three signals. So this one is 0, and the positive sign is here. It is actually K2 multiplied with X1. So this is X1. We bring this signal, multiply with K2, and we use it here. And the third and the last one is the X2 is here. It is being multiplied with K2 plus K3. We can put that even in a single gain. So this is actually the model. Those two model are those two equations are modeled with this block, and this block is actually a coupled two mass spring system. Now we can we can put the initial condition right here, any value, or we can also put in any value here, for example, and we can make the magnitude of the forcing function to be 0, and I can just simulate the system. Right, so this is just a simple simulation. We have two masses, x1 and x2 are the coordinates, and we can start from any initial condition. I can change from positive to a negative. Let's say I start from -1. So this graph would start and you to change to a different shape. Now, once we model it, now let's go back to the theory part and see what are the equation that tells us about the natural frequency. When we do that, so the solution would look like this one. And we can further simplify it. We can remove the cosine term because those terms are not always equal to 0. So it's the term in the bracket which is always equal to 0. So we can rewrite the term in bracket like this one. Now here we have some of the terms are the system parameter like M1, K1, K2. The unknowns that we are interested are capital X1, capital X2, and omega 2. We want to find out the values of those. So if we slightly rearrange this one, we can actually solve this simultaneously by evaluating the determinant of this matrix. So if we just take the determinant of this matrix, put it equal to 0, so we will get this equation in terms of the variable. And this is simply a quadratic equation in omega square. when we calculate it, so omega 1 square and omega 2 square are simple. In terms of other parameter, we can very easily calculate. So by this method, we can actually find out the true natural frequency of any given system, provided we know the system parameter of stiffnesses and masses. So if we find out those frequencies, natural frequency, rest we can find out the ratio, the amplitude ratio. So there are two amplitude ratio. The first amplitude ratio will be maintained by the system, sorry, when both masses are vibrating at the first natural frequency. That will give us the value of R1. Similarly, if we maintain the initial condition with the value of R2, the system will go to the second mode and the vibration will take place at omega n2. This means that we can have a choice. If we maintain the initial values and maintain the ratio of R1, the system will go to vibrate at omega n1. If we just keep the ratio to be fixed at R2 and deciding the initial condition, that will help and will cause the system to move and vibrate in the second mode. So here in this example, I'm using those numerical values for M1 10 kg, M2 12 kg, K1, K2, K3, and using those value, those equation, we can clearly and easily calculate the two natural frequencies of 47.87 radian per second and the second natural frequency of 77.51 radian per second. And using any one value or the other one in any equation, we can clearly and very easily we can find out R1 and R2, which are actually the amplitude ratio at the first natural frequency and the second natural frequency. Now, I would like to see in the simulation when is it possible that the system can vibrate at this first mode and when is it possible that the system vibrate at the second mode. So particularly in one of the example, I would try to maintain the R1 value. R1 is what? By definition, it is x2 divided by x1. If we maintain this ratio, the system should go and vibrate at omega n1. Similarly, if we maintain the R2 ratio, the system should go to the second mode of vibration. So those are the values that we need to maintain in the initial condition and see what happens. Other than this, we will also see some of the force response. So, and now I'm going to switch to the Simulink and try to maintain those values. So now, this is a scope which actually shows combined the mass M1 and M2. I have coupled both the signal with this scope. So here X2 is here. So it is reading X1 and X2. Right now, the initial condition here is 2.3 and here is -1. In order to maintain the ratio of uh, R1 and the R1 is 0.761. So I'm going to keep this R2 to be 0.761 and keeping the X1 as 1. So this actually helped me maintain the R1 ratio. And if I now simulate the system, we can clearly see that now both masses are vibrating with the same frequency and they are completely in phase. So this is actually we have excited the first natural mode by choosing a suitable initial condition in such a manner that the ratio of initial condition is exactly the amplitude ratio. So if I just slightly disturb it, this in phase motion will die out. So the system will go to that upward motion. Now if I want to see the second natural mode, I would like to see that second R2 ratio, and the R2 ratio is minus 1.09. So minus 1.09. So here I have put minus 1.09, here I have put 1. So now the R2 ratio is maintained, and let's see what happens if I simulate this. So we can clearly see that this initial condition, this set, is actually helping us to move the system completely out of phase, and both masses are moving at the same frequency. So this is the second natural mode. And similarly, if we just don't maintain this ratio, I just make it like minus 2, minus 3. So this second mode will again disappear, and it will be a very awkward, uh, it will go to a motion which is very different from the first and the second natural mode. So now coming back to the slides. So this is what we learned. Okay, so I just want to remove this. Okay, so this is actually the scene in which we maintain the value of R1 to be 0.76 here, divide by 1. So in that case, actually, we see that both mass M1 and M2 move in the same, with the same frequency and completely in phase. So negative matches with the negative, positive match with the positive, and it's seem like a slower frequency. Similarly, if we go to the next slide, and okay, I'm actually using this for the first time. So this is actually the second mode. If I maintain the value of R2, then both M1 and M2 will go out of phase, and this will actually help us see the second mode of vibration, second mode of the system. If we don't maintain any R1 or R2 value, and if we just stick to any arbitrary condition, what will happen? We will see a motion like this one. So it's not the first mode, it's not the second mode, it's a very general motion. Now it's the time to apply some force and function. So I will switch again to the Simulink. Now I need to make sure to put all the initial condition back to 0, and then I can make this 0 to be like 5. I want to maintain the 5 Newton, and I want to show you the 5 radian per second. So the system natural frequency is 43, and the second one is 77, but I'm trying to vibrate the M1 at a very slow frequency, and let's see what happens. So if I simulate it, so I need to increase the time limit a bit. So let me make it 5 seconds. And when I do the simulation, so 5 seconds, we can also go for 2 seconds. So this is kind of the vibration. The system want to move fast, but we are vibrating it very slowly. Similarly, we can also vibrate it at 10 radian per second. So the 10 radian per second is a bit faster. So the motion would be like this. And similarly, if we just go and because now we have calculated the natural frequency of this system, we already know that one of the low natural frequency is 43 point. So let me put here 43.87 radian per second. And in this system should resonate, right? So we can see the M1 and the M2 both motion are increasing. So we can see the amplitude are increasing for M1 and M2, and this vibration is at the first natural frequency, and there is no initial condition. This is due to the input force. Similarly, if we just go to the second natural frequency and we make the excitation frequency equals, so that would be 77.51. 77.51 is actually the second natural frequency, and if we want to vibrate this system at that frequency, we can see the system is still resonating and both masses are moving out of phase now. So in the first resonance point, they are moving in phase. At the second, they are moving out of phase. Now let's come back to 43.87, and we would see the in phase motion. Here I just want to show you the beats phenomena. The beats phenomena takes place when the input frequency is very close to the natural frequency but not exactly same. So here I'm just removing this and I'm just moving this system with 43.5, and let's see what happens. So if I run it, now the input frequency is very close to the first natural frequency. And now let me increase this simulation time to 10 seconds. So here we can see a beats phenomena. If I make it 20 seconds, so clearly we can see the beat cycle. This is the case when the input frequency is close to the natural frequency. So now switching back to the PowerPoint, the presentation. So this is the one where the input frequency is 5 radian per second, and this is the one where the input frequency is 20 radian per second. It's not linked with the first natural frequency or the second. So when the system is vibrating at a journal, so we see a very upward motion. And this is the when the input frequency is equal to the first natural frequency, then we see the resonance point. So this is the first resonance point. The system is moving in phase and the amplitudes of both masses are increasing. And this is the second natural frequency. If you vibrate this system at 77.51, the system goes to the second natural frequency, the second mode. System moves out of phase and increasing with time. If you just keep the input frequency to be 43, it's very close to the first natural frequency, then we would see the beats phenomena taking place. So that was all. We actually have developed a mathematical model of 2 degree of freedom system. You can use this system for the analysis. You can play with the stiffness, the masses, the input frequency, and this will actually help you to understand the important concept that is actually linked with the 2 degree of freedom system. So I hope that this will be a good resource for all of my students. Thank you all. Thank you very much.